we can move to the other talk of today. It's a talk from Stefano Scali. Stefano, okay.
Hello.
Stefano did his bachelor study in Siena in physics, and then the master study in Cambridge, always in physics, and then he moved to University of Exeter to do a PhD in open systems. Specifically, he was studying he was at the quantum non-equilibrium group of Janet Anders, and after his PhD, he stayed in Exeter, but is now a postdoc fellow, and he's working on on quantum algorithm, mainly in quantum topological data analysis. And today he's presenting a talk on local master equations bypass the secular approximation, and specifically on the dynamical consequences of that. So please, Stefano, take the floor.
Yes. Sharing. Let me know. Can you see properly?
Yes, I can see full screen of the presentation.
Okay, perfect. So yeah, thank you, the organizer, for inviting me to these series. Yeah, this is a talk about something that is not super new, in the sense that it's something I did in my PhD with Janet Anders, and Luis Correa was a professor here, a lecturer here, and it is related to open quantum systems indeed. So yeah, let's start it. So we are gonna go through the outline of the talk is quite simple. We have a problem, and we want to solve that problem with different tools. I will introduce these tools, which are a set of quantum equations. As Giovanni mentioned, for example, a Lindblad equation is one that we will see. We will call it global master equation to differentiate it in another sense. But we will see that master equation as well. We'll talk about briefly about exceptional points, which are the tools that let us distinguish between these kind of features of the master equations, and we will present some results and conclusions about these four. So here's the justification. So here's the problem. Pasanen, the group of Pasanen in 2009 studied a specific superconducting circuit, which is these. Can you see the cursor? Yes, I guess. So they studied these two resonators in a superconducting setup, resonator 1 and resonator 2, coupled by a conductive coupling, and having a SQUID and a QCR that were kind of allowing different resonances for R2 and a different dissipation for QCR through QCR. So these can be easily represented in terms of open systems as having a couple of paths, right? Two nodes that resonate, which are these R1, R2, with different band frequencies, and then two different coupling constants, the different coupling lambdas to the environment, and an internode coupling. So some coupling term that in these cases is C, right? So we can write it as a system Hamiltonian plus a system a Bath Hamiltonian plus a system Bath Hamiltonian that is sometimes called interaction. So why do they look at these setups? Because they look for exceptional points, right? And these exceptional points, we will see later what they are. But in general, you can think of exceptional points as some sort of critical regime of dissipation. In sense of a damped harmonic oscillator, you can think passing from overdamped to underdamped, you pass through the critical damping regime, and that is an exceptional point in terms of open quantum system, in terms of open systems in general, in terms of non-emission matrices. So they look for these exceptional points because they want to find these quick channel dissipation, because, for example, it's crucial for qubit resetting. And when we are doing the conducting setups, qubit resetting is quite important for quantum computing, right? And they find what they use to model these is the local master equation. But the local master equation is indeed an effective description. So it's a sort of a phenomenological description. So it's taking the two resonators and coupling them kind of independently to the two different baths without accounting for any kind of interactions between the two. So how can we capture the true dynamics of these systems? And that's what we want to answer. So to do this, we go through the master equation derivation, like very kind of hand wavy, just to get the gist of it, just a bit. So we talked about this system Hamiltonian plus Bath Hamiltonian plus system Bath coupling. We remove the coupling from inside for this derivation. So this lambda that was the coupling to the environment between system and Bath, right? We just remove it from H just for clarity, such that this becomes an O of O1 of the coupling, so a constant. So this will be the full system environment state, right? You can describe it as a sort of a you see normal unitary dynamics with SP, right? And we will kind of use this contracted notation of the Lindbladian that is acting on rho on this state, right? And we will start working in interaction picture, and we will remove the interaction picture at the end, again because it's very convenient. So you see that since we are interested only in the system one, in the system state, right, we can trace out of rho, we can trace out the Bath degrees of freedom, and so we will be left with something that is evolved and propagated by L, and then traced out by B, right? So you can write a solution to this equation in this form, right? Just a straight mathematical solution, and then you can iterate this equation. Iterating this equation, so putting these inside rho s plus the environment state, you end up with an equation that is the last one here, which has the initial state, some linear coupling, and some quadratic coupling, and we stop here, right? So this is the first assumption that we take, which is the small coupling assumption. We are left with this equation, and this equation is time non-local and of little practical use, right? So we can reformulate this equation again in terms of just a derivative of how rho evolves, right? It doesn't really change anything by not being dependent by the initial condition anymore. But anyways, so this equation is time non-local because you see there is a t and an s, and so every single time depends on the time of the propagator itself. So it's a kind of a tricky equation still to work with, and of little practical use. Most probably not solvable in this solution in this state, right? So we need to take two strong assumptions. I mean, more than strong, like famous assumptions, which are the Bohr approximation and the Markov approximation. The first one, which is the Bohr approximation, is that the system and the environment weakly interact, right? And how do we translate this? We translate it such that at the initial state, they do not have any correlation, and the propagated state do not have correlations. What does it mean? It means that this state has builds up correlations. It's not that it doesn't build up correlations, but the time scale of this correlation is very quick. It's very quick with respect to the dissipation rate of the entire system, right? So you have these kind of very jiggly correlations that get created, but they decay in time very quickly. And so by these two assumptions, you are left only with this quadratic term, right? And this quadratic term, you see, is still having these issues of L of S, right? That is integrated between 0 and t. And so at this point, we perform the Markov approximation to remove this kind of time non-local problem. And such that we use then the two time correlation functions of the bath decay fast, right, compared to the time scale of the problem. So what happens is that if you take this assumption that we talked about before, and the uncorrelated one, you can end up between a 0 to an infinite kind of integral. So you can extend this integral between, in place of 0 to t, 0 to infinity, and kind of replace s by t minus s. So you can create some sort of an autocorrelation function of the bath, which is formally what this is, an autocorrelation function of the bath, right? So these two assumptions from four, so Born and Markov approximations, give us the Redfield equation. This kind of weird form that is not seen very often is only because we expanded, like we use this contracted form, right, of the Lindbladian. Sorry. So if we take if we kind of expand this contracted form of L that we've seen here, right, this commutator form, you can expand it back and put it back, and you have a bunch of Hamiltonians between system and bath, t and t minus s times, and a bunch of like tensor products because of our Born approximation, right? So at this point, we consider a linear coupling like the one that we've seen in Partanen, because it's the one they use and the one that we can manage actually. So sort of a SB coupling, right? So linear coupling. And then we decompose the system operator in terms of jump operators. This we will see in the next slide properly what this jump operator means in different master equations. But in general, you can decompose S in terms of jump operators. Doing so, you get the normal shape of the Redfield equation that we usually know, where these big gammas are the the autocorrelation functions of the bath, and define the decay rates. The real part of this is the decay rate, and the imaginary part is something that usually we neglect because it's sort of introducing just a lump shift that it doesn't really affect the solution that we want to find. And so we have at this point indeed this Hermitian conjugate and this sort of expanded commutator, right? And we see immediately that this sum is running between the different frequencies, is running over the Bohr frequencies, so over all the channel of dissipations, over all the channels of the jumps that we can perform, right? And this doesn't have any restriction on these form, right? In this Redfield equation, there is no restriction on the jumps. So the first kind of restriction that one could make is a sort of a partial Redfield equation that we call still Redfield equation, because I mean sometimes it's called partial, sometimes it's called not partial, but nonetheless, what happens is that sometimes you can take, it depends on what these jumps are. If there is a different time scale, then at that point you can take this jump to be only the negative ones. So let's say omega plus, one omega is plus, one omega is minus, so kind of different signs of the omegas, right? So that in this way, these terms actually go towards one, but not one, right? This is not zero, but almost zero, because they cancel each other out a bit, right? So this is the real part of the Bath correlation function we were talking about. And so in the end, once you get out of this interaction picture, you have this dynamical equation where you see that the state evolves as the unitary plus a bunch of jump operators making these row jumping around the different frequencies, omega and omega prime, with these sum over with different decay rates, right? The global master equation, which is the Limblad version of it, or what Giovanni mentioned, underpin, like the secular approximation underpins it, right? So what happens is that these omega different signs actually have to be the same omega. So if you take this assumption, so it's sort of a rotating wave approximation, if you want. It's sometimes called rotating wave approximation, but since it can happen also at the level of system size and not full Hamiltonian, sometimes, yeah, you need to call it secular. So what happens is you take out these terms, and you obtain the same equation with less frequencies, right? And then there is the local master equation, which is the phenomenological one, which doesn't take into account any of that, because it has the jump operators are of a completely different shape, right? Indeed, the crucial difference between local and global master equation and Redfield equation is in the jump operators. Once in the jump operators for the global and the Redfield are actually eigen operators of the entire system, okay, the entire system Hamiltonian, while in the local case, as we mentioned, it doesn't take into account any of the internode coupling in the happening in the system, and so these jump operators are eigen operators of the single pair Hamiltonian, so H1 plus H2, the single nodes frequencies, right? So this is the crucial difference. This is phenomenological. This has a bunch of frequencies removed by the secular approximation, and this is the most kind of complete equation. The problems can arise with all of these equations, and the problems are that the Redfield equation and the global equation, first of all, are difficult to scale up. And this is because the eigenoperators that we've seen here, they are eigenoperators of the entire HS. And if these becomes large in terms of nodes, it's hard to find the eigenmodes, right? And so you cannot build the jump operators. In the case of the Redfield equation, it's not completely positive, so you can get out of this positivity, so of this actual physicality. On the other hand, it has a microscopic derivation, which is quite clean. It's a very accurate and applicable. On the global master equation side, it's thermodynamically consistent and is completely positive. So it's a kind of a safe bet, right? But it needs the secular approximation, so it's kind of difficult to justify the secular approximation. And then the local master equation is easily scalable because it doesn't take into account any normal mode, right? It's completely positive, which is good because it's a sort of a Markovian kind of equation. That's not thermalized though, right? So you can find instances where you don't even satisfy the zeroth law of thermodynamics, and can break the second law of thermodynamics. So you can have heat currents that go in the wrong direction. So which one is the best way to describe this other one, right? As we were looking at, this is the local case, and this is the global case. Where do we work and where do we look for exceptional points? We look in the steady state heat current, the regime of consistent steady state heat current, right? So we look in this regime where everything kind of works for every single equation, all right? So in the case of the superconducting qubit, our system was HS plus HB, HSB. HS will be a couple of harmonic oscillators with a linear coupling, and then a linear coupling with the system in the system bath, right? As we were saying, lambda xb. And B, this B is defined by the spectral densities. In general, this G, oh, this should point at G, not B. But anyways, the G depends on the spectral density. So how B kind of interacts with the system and how it responds to the system. And you can see it's sort of a bunch of harmonic oscillators, an infinite kind of caldera-like style harmonic oscillators, right? So this is the system. These are the master equations. How do we look for dynamical differences? You can rewrite this equation, right, that we've seen for rho, this dynamical equation for rho. You can rewrite it for the different moments, for the first order moments and second order moments. In our case, we just need first and second. We are in a Gaussian state. So what happens, we can determine the entire state by first and second order moments, right? So you have these unitary evolution plus the dagger of the of the Limbladian, right? So this D will be replaced. Sorry, this D will be replaced either by the Redfield, by the local, or by the global. And so that you can, if you can do that with first and second order moments, you can set up a closed set of differential equations that you can solve. So if it's a first order set of differential equation, you can write it in matrix form. And at this point, you have a non-emission matrix you deal with, right? And what we talked about is that in parameter space, there exist these exceptional points, which are these non-emission degeneracies, right? And so you have these eigenvalues that coalesce. You have a square root singularity, for example, a square root in the solution that kind of goes to zero. And at the same time, the eigenvectors that correspond to that to those eigenvalues as well coalesce. And this is what an exceptional point is, right? So we look at these two. So as I said, you have three sets of matrices, and you can look for exceptional points in these three sets of matrices. How do we sense the exceptional point? Well, it's kind of simple in that sense, because it's condition number of the matrix of the eigenvectors of the matrix we consider, right? You take the matrix, you take the eigenvectors. Since two of them coalesce, the condition number depends on the v minus 1. Two of them coalesced, the v minus 1, the norm of v minus 1 explodes, because you have a singularity in it, right? So two of these coalesce. And so what happens is just this norm explodes, so you have an infinite condition number at the exceptional point. So these are the results. You have a local master equation that shows a line of infinite condition number, global master equation that doesn't show any, and the Redfield equation that does show the same line. This same line coincides with the red dotted, which is the analytical solution that we can find in resonance. So this thing, right, has consequences. The fact that there are no exceptional points in this regime has consequences in the specific thermodynamical consequences. In the steady state heat current, we see that exceptional points, nothing happens, right? You see these the steady state heat current, the blue and the hot, the two different current, kind of do not sense anything at the exceptional point, right? Let's not talk about physics. Rigidity is some way to see if there is an exceptional point, and there is an exceptional point. But you see both the global master equation and the local master equation like behave correctly in steady state. But the transient heat current, you can see they're very, very far apart, right? So this is at the exceptional point. You see that there are dynamical consequences. How do we explain that? This is very quick. You take the dissipator of the Redfield equation. You can expand it in internode coupling of this, right? And once you expand it and you take the 0th order in the low K limit, so you go in the low K limit, low internode coupling, you can recover the the local dissipators. So what happens, you effectively go into the local picture once you go in very low internal coupling. And these are our findings, which is, to summarize, is kind of the local master equation in general is regarded as a sort of a limiting case of the global master equation. And this is kind of easily understood because it creates a dynamical semigroup, right? So it's a CPTP map. So it's something that is positive and trace preserving, right? And so it's something that comes kind of natural. But the problem is that we found out that this is not the case. It is more the case that the local master equation is indeed the low K limit of the Redfield equation, which doesn't include the circular approximation, right? And so if we're talking about internal coupling low internal coupling, at that point, probably you have a good chance that the local master equation is indeed your best approach. And it comes nicely to the in hand, just because it's completely positive and it's scalable. It's very simple to use, right? And it's kind of derived from something that is microscopically derived. So it's kind of okay, kind of a good news. Yeah, that's it. Thank you.
Thank you very much, Stefano, for the nice talk. Are there comments or questions? I have one concerning the Markov approximation of the interaction. Yeah. I mean, in the system that you have in mind, the system of the squid, is it something that you can, in a sense, it is an approximation that you can trust on, or is something that could have also some, or could give also some surprise?
Well, having non-Markovian behavior, it's always possible. In the sense, in an actual system, I'm not an expert of the actual experimental setup, so I'm not sure if they experienced or they kind of had to trace out some non-Markovian effect happening. But in general, if you, since they have a very tunable setup, what happens is that if you can hit the right spot of in parameter space, so you can work in the regime where your couplings are right, you have a fast dissipation or even a longer dissipation. This is a sort of an approximation that holds, and that holds quite strongly. Yeah, it's also a matter of tuning sort of the coupling to the environment. So if you manage to tune the coupling to the environment to the weak enough regime, then it's gonna hold. Yeah.
Okay, thank you. Any other question or comments?
I have a curiosity, if you don't mind. I didn't very well understood the last part when you compared the appearance of the exception point in all the different master equations. But it's like these features that some exceptional point can appear in the local one, in the Redfield one, are dependent on the systems, or can you like find out some general theorems that link the appearance of an exceptional point in one of the master equation to the others?
In general, they are dependent on the system. Like in general, if you had only two nodes, it will be here where they are in these analytical points in parameter space. If you had three nodes, they would still appear, because we are talking about still harmonic oscillators. and they kind of behave like frequency filters. And if you had qubits, they still would have them. They still would have exception points. They would have them in different places. Like probably you will need to go to resonance anyways, but different dissipation strengths.
Okay, but can you somehow like be sure that, for example, you have an exceptional point in the Redfield master equation, then it will appear in the local one, or something like that?
You mean if this is always the case?
Yeah, exactly. If it is
okay, this is always the case in the low K regime, not always.
Okay.
So if you go in the low K regime, then which is where we are working on, yes, you will always have these in the case of frequency filters. Yes. In other cases, well, it's yes, it's a bold, would be a bold statement. So I don't want to.
No. Okay. Thank you.
No worries.
Any other question or comment? So if not, let's thank again Stefano and Giovanni. And it is now time to close the seminar session. And as usual, there will be another session next month, the second Thursday of the month. So see you, or see some of you next month. Thank you very much for participating, and bye-bye to all of you.